with homework questions. Maybe we'll start class with homework questions. That way, she won't miss any lecture anyway. Apparently I don't know my password. Of course, I make me change it so often, it wouldn't surprise me if I never knew my password. Yeah, I press download, but then it would tell me that I'm not certified to make changes on this computer, so they just won't ever make changes. They'll just sit here getting older and more obsolete. Do you have any questions?
Yes, F4.
Excellent. Give us something to do. Couldn't be so happy. Happy day. Hello? Someone there? Alright, what homework?
The one that's due today is chapter 13.
Temperature?
Yeah.
Which numbers?
4? There were 4, yeah.
Cryogenic vacuum pump works by condensing vapors onto some absorbent medium. This is an efficient and clean way to pump a system in a research environment. The term cryo means cold, therefore these types of vacuum pumps contain a refrigerant cycle to cool the internal parts. The temperature difference between the inside and outside of a typical cryogenic pump is 315 degrees Celsius. Derive an expression to convert this difference into Fahrenheit and express the answer below. So, must derive an expression, huh? Derive an expression from difference into Fahrenheit. Oh, okay. So there's a delta T of 315 degrees Celsius, and what they're telling us here is that we should use the equations that we are familiar with in the book. So open up the book here and look at the equations really quick. So in our temperature this is chapter 3. Okay, good. Right about goodness, it's way back. We're going to the way back. Okay, so we're going into the very beginning of the chapter and we're talking about different temperature scales right here, and then on this next page, they give us some conversions. Right? What they want to do is what they want us to do is to take this one that changes things from Celsius to Fahrenheit and change it into a delta T, a delta Celsius to Fahrenheit, right? Not that big a deal, really. The equation looks like, I wonder if that'll copy into picture creation there. Let's check it out. Maybe not. Oh, come on. This computer is killing me. Who cares? Well, 9 Phys T plus 32, right? So let's go here and let's, my mouse is stuck. Okay. Alright, so we have T in Fahrenheit equals 9 fifths, was it? T in Celsius.
Yep.
Temperature, Fahrenheit, equals 9 fifths temperature in Celsius plus 32 degrees, right? Well, that's great. But what we want is we want to change, we want to be able to put a change in temperature in here. And really this is technically not the way to do it. But this is good enough. Essentially your answer right there. But the way that you actually go about doing this is you write this equation twice. Once for the temperature initial in Fahrenheit, once for the temperature final in Fahrenheit, and then you take the difference of both of those equations, and what you're going to end up with in the end is 9 fifths times temperature final in Celsius minus temperature initial in Celsius in place of temperature C plus 32 degrees, right? And then, oh, actually there's one other thing that's going to change. Because both of these equations are going to have a plus 32 in them, that's going to go away.
Oh, okay.
Right?
That's probably what I was
So the plus 32 goes away. Because when you're talking about a difference, you don't really care about the offset. You only care about the difference. So all you have to do is, so when you take the difference, the 32 goes away, and you just end up with this right here. Right? So we go back to our homework, and we go ahead and write that in. And we're supposed to let our, where's our math?
Actually, we just put in the answer, what it would be after we did it.
Derive an expression. Oh, and express the answer. Okay. Yeah, so the 32 goes away when you take that difference, right? And maybe that's what they talked about in the hint.
If that works.
Okay, good. Number 10, maybe?
Yeah. Yeah, this one, I thought I was on it right every time I put it.
So you lower the temperature of a sample of liquid carbon disulfide from -2.1 degrees Celsius till its volume contracts by 0.505% of its initial value. What is the final temperature of the substance? Coefficient of volume expansion for carbon disulfide is 1.5 times 10⁻³ per degree Celsius. So whenever you're doing this kind of a problem, let's see. Oh, I erased the whole thing. Erase or just go to the next page. Okay. Anyway, we have this change in length thing going on, right? Equals m. No, that's not right. It's equal to, I can't remember the equation. it's equal to the, what's the, is it alpha, or what's the,
This would be like a, it looks like a capital V almost, I forgot the name.
beta?
Yeah. It would be changing volume, though.
Oh, we're doing change in volume?
Yeah.
Oh, volume. Okay, so it's actually gamma. They choose gamma times delta T times the original length, right? Or this original volume.
Okay.
So this is delta V. I think that's the equation, does it look right?
Yeah, very much.
Okay, so what is the delta V? The delta V is how much the volume changes. Well, in this problem it says that it changes by 0.515%, right? Or something like that. At 505% of its original value. Well, what is that equal to? Well, it's equal to 0.0505, right? That's 5.505% times what?
Original volume.
Times original volume, right? Equals gamma, which we know, and delta T, which we don't know. What don't we know? I don't even know what we don't know. What don't we know?
We know everything, just there.
What's the final temperature of the substance?
Well, when I use temperature here, do I convert to Kelvin, basically? Do I have to do that?
Nope, you can do it in degrees Celsius because it's a change in temperature. When it's a change in temperature, all you need is the difference, and the difference is the same in Kelvin as it would be in Celsius.
Okay.
Because they have the same size degrees, right?
Yep.
Same size steps. So in this problem, the V0 goes away because you just divide it on both sides.
We're trying to
And
find
you just divide this number by gamma, which is the number they give you, and you get the change in temperature.
Okay. Now, when I did it, every single time my change in temperature was below absolute zero, so I knew my answer was wrong. That's because my coefficient is so small, it divides out.
1.15 times 10, well, I'm getting 0.00505 divided by 0.10.
Oh, wait, I did it differently though. Okay.
0.00115, right?
I'll try it different. I think I know what I did wrong, actually. I thought too hard.
It'll be a small number, and the change in temperature will be small, but it won't go below. I mean, it's not going to be, the change in temperature won't, to go below absolute, you don't even know the starting temperature, so you can't possibly know if it's going to go below.
Well, we know the starting temperature, actually. We don't try to find it.
Oh, you do know starting?
Yeah.
Oh, you do. But it's going to be a small number. It's only going to go down by a fraction of a percent.
Okay. I think what I did differently, I thought since it goes down that percentage, it just goes down that tiny percent, it stays 99% of the same instead, and I use that number instead of the small percentage.
Oh, no, use the small. Because they want to know what is the change, and that's the change. They don't want to know the new volume. Right? Okay. Is number 12 the next one?
Yep.
Volumeric expansion coefficients of simple materials are often well cataloged. However, the thermal expansion coefficient, beta, of a human body is less well known. It can affect the human body's specific gravity and therefore measurements of its body fat ratio. Human body changes with each time. So, suppose a human body of weight W0 on dry land is placed on a scale while completely immersed in formaldehyde at temperature T1. Once the temperature increases delta T, the scale reading drops by delta W. Derive an expression for beta in terms of delta T, W0, and delta W by assuming the ratio of the formaldehyde rho F and the initial density of the body rho 0 is R equals rho F equals rho 0. Assume also that rho F does not change when heated. So this is actually a don't do this. Don't immerse yourself in formaldehyde, by the way. This is for a dead body, or one that will be dead after they do this experiment. But this is partly a expansion in heat problem and also partly a Archimedes law problem, right? Oh, sorry, my eye hurts all of a sudden. Nice, I don't know what went on there. I do apologize for yawning so much. I've actually been ill and I've lost 20 pounds in the past few weeks. Which, you know, is not a bad thing for a fat person like me, but it also just makes you very tired to lose weight because of sickness. So anyway, all right, so let's take a look at this problem. Let's go into the creations. And we've got essentially our human body, which I'm going to represent as a sphere or some blob. And it's going to have mass or weight 0. And then when we put it in the formaldehyde, it's going to have a different weight. It's going to change its weight. It's going to have a new weight, which we're going to call, it's going to be equal to weight 0 minus delta weight, right? And the delta weight is the thing that we're interested in. That's going to tell us the information we need to know. Because the delta weight is going to be due to a couple of different forces. First of all, there's going to be the buoyant force upward, right?
Yep.
It's going to be reducing the weight, so we're going to have buoyant force. But within the buoyant force you have, remember, you have the volume of the body times the rho of the formaldehyde times gravity, right? And the volume of the body actually changes. Out here, the volume of the body, the density, or the density of the body is one thing. In here, the density of the body is another thing. And so, and remember that density is equal to mass divided by volume, right? And so that means that volume is equal to mass divided by density, right? And so in place of volume here, we're going to put in the mass of the body divided by the density, the new density, because this one's going to be the changed density of the body in the fluid. And so that's going to be, and I'm going to actually write that as the density of the body minus the change in density, because it's going to change its density. And in fact, actually, let's not even do that. That's just confusing. Because we can actually calculate this whole thing as one. We don't need to even know the mass of the body. This whole thing is going to be calculated, remember, by using what we learned about the volume, change in volume. Because the volume of the body, when it's inside the fluid, is going to be the original volume of the body minus the change in the volume of the body, right? So it'll be volume body minus change in volume of the body times rho of the formaldehyde times gravity. Now, the change, this delta V here, can be calculated by using our equation. Our equation looks like, instead of delta V, it's going to be the gamma times delta T times the original volume body, right? So we have this thing in place of our original volume. And then that's multiplied by the formaldehyde density and gravity. And that'll tell us our buoyant force, right?
Yeah.
So let's go back and look at the problem real quick and make sure we're barking up the right tree. Here, we have volumetric expansion, suppose human body. We have the original weight on dry land. On a scale completely immersed in formaldehyde,
Yeah, what was I trying?
Temperature increases, let's see here. Okay, so we're not quite on the right track because we went outside of the tank to inside of the tank, right?
Oh, yeah.
Ours went from outside the tank inside the tank. Theirs is actually inside the tank both times. And they changed the temperature in the tank, right? So this is T1 and this is T2, temperature of this thing. And let's see what it says here. Human body, we have an expression in terms of, and it's a weight is weight 0 on dry land. So we're going to have temperature 1, temperature 2. Well, they're using beta, not gamma. That's fine too. We'll use beta. Does the equation use? I don't remember what the equation uses for expansion. Let's go look at that.
It's beta used
For volume expansion.
Yeah.
So 2 alpha and beta. So let's do another page of this really quick and look at this a little bit differently. Let's just look at the tank. We put our thing in there that has weight 0 normally pushing down, and then it has buoyant force pushing up, right? Where the buoyant force is equal to the volume times rho of the formaldehyde times gravity. This is the volume of the body. And the volume of the body at each temperature has its own thing going on. So the volume of the body in general is going to be equal. Now let's go back out here and see what they've given us. Rho naught is the initial density of the body. So they give us the initial density of the body. So that's helpful. So volume of the body is equal to density, is equal to mass over density, and they give us mass, right? No, they give us weight though, let's get that. So they give us weight. So it's mass over density, right? Body. Well, mass of the body, the mass of the body is equal to the weight of the body divided by g, right?
Yep.
And the weight of the body is W0 over rho body g, right? So that's volume body, and so that ends up being here. We end up with weight 0, rho f g over rho body g. G's cancel. And this would be the buoyant force if this thing hadn't heated up at all.
Yeah.
Right? So what changes if it heats up? The density changes, right?
Yeah.
This part, essentially the density changes because the volume changes. And so initial density of the body rho b is that initial density dry on dry land or in the water? It doesn't really say. think I'm going to have to say yeah, I'm going to have to say that the density rho B here in this question is when they put them in the first one. Comes to thermal equilibrium in the first tank. So that's just from reading the hint, that's going to tell me that. So essentially this is correct for the body in the first tank at temperature 1. At temperature 2, what changes is the density of the body. Density formaldehyde doesn't change, it's just this number that changes, right? Excuse me. So how does it change is the question. It changes because the volume of the body changes. So I'm just going to call the volume of the body in tank 2 volume 2. And that's going to equal the original volume, which is VB, right?
Yeah.
Times beta times delta T, right?
Correct.
VB we already have is this, so it's going to equal the original weight over rho BG, right?
Yeah.
Times beta times the delta T. And that means that the buoyant force on the second one, we'll call force 2, we'll call it, is going to equal this one here times rho F times G. So the G's are going to cancel. We'll end up with weight times beta times delta T times rho F all over rho B, right?
Yeah.
So now that's our second buoyant force. So what's the difference between their weights? What's the difference between the buoyant forces, essentially? Times, well, no, that is just it.
I put it in terms of beta, and then also gives us R equals.
But yeah, because this is R right here.
Okay.
Rho F over rho B is R, right?
Yeah.
So that would be called, instead of having this ratio in here, this would be W naught beta delta T times R.
Okay. And then we just
And
solve
this one would be the
beta
same.
of both of them.
What's that?
We put it in terms of beta, we just solve for beta on one side, or?
No, this is in terms of beta.
Okay.
So the difference, what you're going to do is you're just going to take this number, you're going to take this thing minus this thing,
Okay.
and that'll be in terms of, so it'll be W naught rho, W naught times R minus W naught beta delta T times R, and then you can simplify it if you want to. Or you actually, let's see, it's going to weigh less here, so yeah, that is the way it's done. You know, more minus this. So, yeah. Okay, I'm going to connect to Imperial here, or Valentine rather. See if they're done with their class yet. Okay, well apparently they're done with their class, but we don't have students. Okay, well. Alright, well let's get on. Let's do 30 minutes of problems. Let's do some chapter review here, chapter studying. We're on to chapter 14 now, I believe, right? In the book. Getting very close to the end. If you remember, we get through heat, and then we do some waves, sound, and we're done. So we're pretty close here. Heat and heat transfer methods. We spend a few chapters doing heat. And here they show a person and the earth, and both things We're transferring heat all the time. Very interesting stuff, actually. The first thing to do is actually to define what heat is, and so we understand the difference between heat and temperature, for example. Heat is defined as the spontaneous transfer of energy due to a temperature difference between materials or between systems. So heat is actually a type of energy, but it's always a transfer of energy. Heat is not just something that is in something. We say this is full of heat. That's not what heat is. That is what we call internal or thermal energy. Heat is actually the movement. It's actually the act of energy moving from one thing to another. It is energy, but it is a transfer of energy. So, temperature, again, is a measurement of the internal energy of an object. It is not energy itself. Just like newtons are not force, they are a way of measuring force, right? They are a unit for measuring force. Temperature is a way of using a unit or a device to measure internal energy. The actual internal thermal energy of an object has to be calculated, usually, from theory. I mean, it can be measured using a thermometer, but to really understand, you can get a representation of it measuring its temperature. But the temperature itself only tells you part of the story because, for example, a lasagna that is at 200 degrees holds a lot less energy than a brick of copper that's at 200 degrees. And a small slice of lasagna at 200 degrees holds a lot less energy than an entire pan of lasagna. So mass is important, what it's made of is important when it comes to the actual energy, whereas temperature just gives you part of the story. It is a way of starting the process of figuring out how much energy is inside. Well, if heat is a type of energy, then it can be measured in all the same units that we measure energy in. It can be measured in joules, it can be measured in calories, kilocalories and kilowatt hours. Anything that we use to measure energy can be used as a unit for heat or heat transfer. But you can also measure. You can begin the measuring process by measuring the change in temperature as heat is transferred from object to object. It just, remember, it doesn't tell you the whole story. It's just one measurement that gives you some information. You still need to know what the objects or the systems are made of and how much mass there is in them, and so on and so forth. So here is an example of heat transfer. You have a soft drink and you have ice, and they have different temperatures. Generally, your ice is colder than your soft drink. And you throw the ice on the soft drink, or the soft drink in the ice, or whatever else, and the contact allows them to exchange energy. And as they exchange energy, if the soda is cooler or warmer than the ice, then the soda will cool off and the ice will melt, and then the water that the ice becomes will start changing temperature, and so on and so forth. And eventually they'll come to equilibrium, where they're the same temperature, where temperature of the can is equal to temperature of the ice. Because at that point there won't be any more heat transfer, because remember that heat is the spontaneous flow of energy from objects of hot temperature to objects of colder temperature. So temperature is very important when it comes to heat transfer and when it comes to internal energy, but it's not the whole story. It's just part of it. It tells us a lot of things, gives us information, not everything. And how do we know that we can use joules and calories? You know, joules we used for kinetic energy and potential energy and spring potential energy. We didn't use them for heat energy. How do we know this is the same kind of stuff, the same kind of energy? Well, a great experiment done by Joule himself actually was able to prove that movement energy and heat energy are the same. And this is the experiment that he did. He had this device that had masses connected to pulleys, connected to a drum, that were connected to this paddle stirring system inside this big vat of liquid. And as he cranked on this crank up at the top, he was able to raise the mass on one side and lower the mass on the other. Or it depends on how you design it, but you can raise both masses up and then let it go and let the masses fall. But in any case, what happens is that you're putting energy into the system that you can measure by the height that these masses fall. And so you know the change in potential energy of the system. It went from these masses being at a certain height to them being at a lower height. And then that energy was turned into kinetic energy in the paddles inside the liquid. The paddles inside the liquid transferred their kinetic energy into the liquid in the form of heat through friction and stirring and other things like this, and there was a change in temperature. That change in temperature was measurable. And if you're very careful and you keep everything isolated, you can actually show that there is an equivalence here, that there is a conservation of energy going on, and which is nice. So anyway, that was Joule's famous experiment. So, how are temperature and heat related? They're related by the material and the mass of the material involved. The type of stuff and how much of it. Right? Of course, if you have more stuff, you assume that it could hold more thermal energy. More heat could flow into it or flow out of it. And of course, different types of materials are just more capable of, or more or less capable of, holding or transferring heat. And that just is a consequence of how they're made and their structure and densities and other things like this. So, in the end, it comes out fairly simply that the amount of heat that is exchanged between two objects is equal to the mass. We said it would be and have something to do with the mass. And it's also dependent on the change in temperature, so those two things multiply together. And then there's some other factor that takes into account the material, which we call the specific heat of the material, C. And it's a very simple equation. The amount of heat equals mass times specific heat times change in temperature. And if you keep everything isolated, you keep your system insulated from the surroundings so that no heat can escape your system or enter your system, then that equation will be absolutely true. And the amount of heat that leaves one object will be the amount of heat that goes into the other object as you go back and forth between two objects with heat. So here's a very simple example. We have a half-kilogram aluminum pan on a stove. It's being used to heat 0.250 liters of water from 20 degrees Celsius to 80 degrees Celsius. How much heat is required? Well, okay, first of all, they've given us a change in temperature, 20 degrees to 80 degrees. They've given us a volume, 0.250 liters of water. That volume will help us to figure out how much mass of water we have. And if we change this amount of water, 0.250 liters from 20 degrees to 80 degrees Celsius, we should be able to use that equation with the proper specific heat, right? So, first we calculate our change in temperature. It turns out to be 60 degrees, final mass initial. Then we calculate the mass of the water, 0.250 times 1,000 kilograms per meter cubed. 1 liter is 1,000th of a meter cubed, so it ends up being 0.250 kilograms. Then we calculate the heat transfer to the water by just plugging these things in. It turns out that the specific heat of water is 4,186 joules per kilogram degree Celsius, which is actually quite high. Water can hold a lot of heat. Well, it can have a lot of heat transferred into it, right? 4,186 joules for every kilogram that you have and every degree Celsius that you change the water. So we use our mass, we put in our C for water, that's for liquid water, it's different when it's ice and it's different when it's steam. And then we put in our change in temperature, we get 62.8 kilojoules of energy that has been transferred into the water, right? It's the heat transfer to water. And then calculate the heat transfer to the aluminum. Well, the aluminum has a different mass. They told us what it was. Has a different C. We can look it up, and it has the same temperature. 27 times 10 to the fourth kilojoules. Different amount of heat. Then we're going to compare the percentage of heat going in the pan versus the water. So we get the total heat involved, and we take the pan heat over the total heat, and we get 30%. And for the water, we get 69.9%. So to raise aluminum 60 degrees only requires 27 kilojoules, but to raise water, 62.8 kilojoules. It takes a lot more energy to change the temperature of water than it does to change the temperature of aluminum. And generally, when you're cooking, that's what you like. Why do you want your pan to take very little heat, to require very little heat to change its temperature? It gets hotter faster, right? In other words, it takes the heat from the stove and it transfers it into the water much more quickly, right? And so aluminum is it's good for that. Copper is even better, but why wouldn't you use copper in a kitchen? Actually, aluminum bends far more easily than copper. Well, not necessarily. It depends on your relative alloys of aluminum that you use. But the reason you don't want to use copper is because it's expensive. So a copper pan and an aluminum pan of the same size, the copper pan will cost 10 times what the aluminum pan costs. So while aluminum doesn't quite do as good, it's much better for kitchens because it's just so much cheaper. Cast iron is another one that's quite good, but we don't use that one because it's heavy. Copper is also heavy. Very expensive kitchens. If you go to a kitchen of a millionaire, they'll have all their pots will be copper. And because they're wonderful to cook in. They heat up very quickly. But you go into an industrial kitchen in any restaurant in the world, and they'll all be aluminum. It's just the way it is. Very few of them will have some cast iron for very specialty cooking, and maybe some other things for specialties. But the vast majority of the stuff you'll see in industrial kitchens will be aluminum for speed of cooking and lightweight and low cost. Because restaurant business is not a high percentage business. But anyway, why do you think that we use water to cook in? We use aluminum pots, but why do we cook in water?
Stays.
What's that?
Stays.
It stays hot. You can put a lot of energy into it, and so anything that you're cooking in it, like meat or pasta or anything else, will have a lot of energy available to cook it, right? And it stays hot for a long time, right? This is not true of a lot of things. It's not true of oil. When you fry things, they cool rather rapidly, whereas you cook things in water and they stay hot for a much longer time. And people like fried things because they're crispy and crunchy and hot grease tastes good. But cook something in wine and compare the taste. It's way better. Okay, so calculate the temperature increase from work done on a substance. So this is now a little bit different. Instead of just saying we change the temperature, we're going to actually tell you how we change the temperature. We're going to have truck brakes are overheating as they go downhill. So we have truck brakes are used to control speed on a downhill run, and they're going to do some work, and they're going to convert gravitational potential energy into increased internal energy, in other words, higher temperature of the brakes. The conversion prevents the gravitational potential energy from being converted into kinetic energy of the truck. Problem is that the mass of the truck is large compared with the brake material. Temperature increase may occur too fast. And that's the problem with brakes. If your temperature increases too fast, they melt, and then your brakes aren't there anymore, and you're dead, right? You don't have any brakes. So you have 100 kilograms of brake material. The specific heat is 800 joules per kilogram. Now you can imagine that this number right here is really important for brakes, and also this number. If you've ever purchased brakes before for a car, the expensive ones are massive, they're huge, they're thicker, and they're made of special materials. The cheaper ones are thinner and made of cheap materials. So, we're going to talk if the material retains 10% of the energy from a 10,000 kilogram truck. So what that means is that the brakes heat up, but only 10% of the heat remains in the brakes. The rest of it gets bled off into the atmosphere around them. So you're only keeping 10% of it. You have a 10,000 kilogram truck descending 75 meters vertical displacement at a constant speed. Okay? So the first thing we need to know is how much energy that amounts to. So the change in potential energy is going to be 10,000 times 9.8 meters per second. That's m times g times the actual height change. And that's how much energy the truck has at the top of the hill. And we're only going to use 10% of that. Right? Where do they do the 10%? Oh, they don't. Why not?
They did it already.
What's that?
How can they do it already today?
Mass, 10,000 kilogram truck.
They changed it to 1,000 next part.
If the material retains 10% of the energy, I'm not seeing where they are using only 10% of the energy.
Oh, I forgot.
Yeah, I don't know either. So anyway, they're not using that 10% anymore. Or it should be right here. You should multiply this number by 10% and you would get 7.35 times 10 to the 5 joules. And with that number in here, in the equation where they rearrange the equation for the heat, so they have temperature, the heat is equal to the potential energy, right? And of course the heat is also equal to mc delta T, so they rearrange that to get delta T, and then they put their heat, their mgh up here. There should be a 0.1 multiplying that. And then you would get 9.2 degrees Celsius of delta, of change in temperature. But they don't do that. They should have. But anyway, to have your brakes at the boiling point of water is actually probably too hot. But this is actually why, because when you have your brakes that hot, what begins to happen is the brake material does start to essentially evaporate. And it starts to degrade. When you get that hot, you're shaving it down, you're taking lots of material off of the brakes. And so they use engine brakes. In a diesel engine, you can actually reverse the vacuum in your cylinders so that instead of driving the wheels, it actually slows the wheels. It's slow, and that's when you hear them coming down the hills and they go brrrr, that really loud sound that's called the engine brakes, and that's where they reverse the vacuum in their cylinders. Hybrid cars actually use the heat on their brakes, and they use a thing called a Peltier device. And a Peltier device, when you get it hot on one side and cold on the other, it creates a voltage and drives a current, so you can actually charge your batteries using the heat on your brakes. Also, some electric cars, like the Tesla out of California, uses active braking technology, which is where they use the actual electric motor to slow down the car. But when you're slowing down the car using the motor, it turns into a generator and they charge the brakes. And trains do that too. Trains, when they're going down hills, they'll just they reverse the electric polarity on their engine motors, and those motors become generators and they charge their batteries as they're going down hills. and they slow the locomotive down instead of using brakes. Anyway, here's a bunch of specific heats for different materials. They have the specific heats in two sets of units, one in joules per kilogram degree Celsius and one in kilocalories per kilogram degree Celsius. And you can see different things that have different specific heats. You know, water, like we said before, is, where is water?
Okay.
There it is, 4186, right? And it's pretty much the highest thing on this list. Builds a lot of energy. Ice does a pretty good job too, but not nearly as well as liquid water. Gases generally hold a little bit less. Steam is still pretty high up there. Final temperature when heat is transferred between two bodies. So pouring cold water into a hot pan. So they're pouring 0.25 kilograms of 20-degree water into a 5-kilogram aluminum pan with 150 degrees Celsius temperature. And essentially what you're going to do here is you're going to say, well, the heat that leaves the hot one has to equal the temperature that enters the cold one. Or not the temperature, the heat, right? The heat leaving the hot thing has to equal the heat entering the cold thing, as long as your system is isolated or insulated from surroundings, right? So you have two equations that are both mc delta t, where the delta t is the same for each except reverse in sign, and so that's why they put in that absolute value. But the m and the c are different for each, right? And so it's really not that hard in the end. You just solve that equation where one is equal to the negative of the other with different masses and different specific heats. You get an equation that looks kind of like this, and just plug in the numbers, and you can calculate that change in temperature. The temperature final is the same in each of these because they come to equilibrium. So you have one that goes from 20 degrees Celsius to temperature final, one goes from 150 degrees Celsius to temperature final, excuse me. They're negatives of each other. So this one's a positive one, this one's a negative one, and they have different, of course, masses and different specific heats. Solving this equation is not trivial, it's kind of messy, but you can do that. All right, I'm going to take a break here for a few minutes. I need to get a drink, walk around a bit, and we'll come back and get into calorimetry, which is what we just kind of had a preview of in that last problem. I'll be right back. I'll be back in 10 minutes. Okay. Calorimetry. Calorimetry being the measurement of energy as it goes back and forth between objects in the form of heat. It's kind of like bookkeeping. And we just did our first problem in it. I mean, I can't get my other screen up and going again, but that's all right. So, that's what we're going to be doing here for the most part. We're going to add in one more little wrench into the system. I'm going to throw in a little curveball here. And that is that when things change temperature, they sometimes actually change their nature. For example, ice can change into liquid as it heats, and liquid can turn into gas as it heats, and so on and so forth. And when they do that, when substances melt or vaporize or freeze or condense, the amount of heat that goes in and out of them is actually different than when they're changing temperature. And they don't change temperatures while they're doing this. And this is true mostly of materials that are homogeneous, made of one material, like water. If it's all H2O, all the molecules are H2O molecules, then it behaves these kind of rules. But, so, I mean, the two main features of melting, freezing, vaporizing, and condensing are that during those processes, all of the energy that is transferred into or out of the material is going into changing the phase or changing the properties of the material. And it's not changing temperature, it's just changing its phase. And there's a different way of calculating that amount of energy. And it has nothing to do with changing temperature, since they're not changing temperature. It only has to do with the mass and what the material is. And so we call this the latent heat. So the last Q equation we had was called specific heat, and it had to do with change in temperature. So when things are changing temperature, you use specific heat, but when you're changing phase, you use latent heat. And there's a latent heat of fusion, which is for melting and freezing. And there's a latent heat of vaporization, which is for vaporizing and condensing. So it doesn't matter which way you're going, it's the same amount of energy. And it's the L that you're going to look up in a table now. And that table is on this next page here. No, maybe not. Here it is. So you have for different substances, for helium, for example, you have a latent heat of fusion, latent heat of vaporization. They also tell you the temperature at which these things happen when there's normal pressures around. So for helium, it's very low temperature. It's very, very cold. You get something that we're more used to, like water, at 0 degrees, it changes from ice to liquid, and it has a latent heat of fusion 11.8 kilojoules per kilogram. And at 100 degrees, it changes from liquid to gas, and it has 2,256 kilojoules per kilogram. You can see right away that there's a lot of energy when you boil something off. And that's actually very apparent to people who have ever lifted a lid off of boiling water. You can burn your hands, actually, or your face that way quite easily. And it's not the stuff that you see, it's not the water vapor that's the dangerous part, it's the steam. Because the steam is carrying away all of that energy. And steam is invisible. If you've ever boiled water in a teapot, you'll notice that right next to the little spout on the teapot when it's boiling, there's nothing you can see. But just a fraction of an inch after that, a fraction of an inch above the teapot, you start to see this white steam, as we call it, which is not actually steam. The steam is the part you can't see. That's the dangerous stuff. That will give you third-degree burns if you touch it. So don't touch it. The vapor, it can be hot, but it's not carrying nearly the energy that the steam is because it's lost 2,256 kilojoules per kilogram of energy as it turned back into little droplets in the air. So steam holds a lot of energy, and that's why it takes so long for water to boil. You have to first get it to 100 degrees, and then you have to put in this much energy for every kilogram of water you have. It's a lot of energy. So, this is a diagram that we should pay attention to. This is our temperature versus heat diagram, temperature energy diagram for water. And you can see what happens here as you're changing the temperature of ice. You're coming from, we're starting at negative 20 degrees Celsius, and ice can get colder than that. You can go all the way down to absolute zero, theoretically. But anyway, you have ice that goes colder and colder and colder. Excuse me. And then once you warm it up and you get up to 0 degrees, you start to get liquid water mixed with your ice. The ice begins to melt. And in that whole time, you're putting a little bit more energy in. So you've got this energy that we put in here, and we've reached this point where it's ice and water mixed. Then you have to put in this much more energy, which turns out to be, 100 and something calories per gram. So you put in some energy, and it's not very much you have to put in. It's just this short little path before it's all water, and you can start changing the temperature of the water. And you just keep heating it up, and the water gets warmer and warmer and warmer until it gets to be 100 degrees Celsius. And then it starts to form little bubbles in it that are steam bubbles. Usually in a pan that's at the bottom of the pan, because that's where all the heat is coming in. That's where the transfer of heat is taking place. But if it's in a cloud, it can happen anywhere. But the bubbles begin to form, and those bubbles are actually water gas bubbles. They're steam bubbles. And those steam bubbles are carrying energy. And as you are boiling off the water, turning it into steam, you're bubbling and bubbling and bubbling. And look how much energy you have to put in before you can bubble it all away. So much more than it takes to melt the ice. You're putting in so much energy to boil off all that water. Same amount of water as you melted here, but a lot more energy to do it, almost 10 times as much. And then once it becomes steam, you can continue to heat it. You can get it hotter and hotter and hotter and hotter. Now, why is it that it does these things? Why do different materials have different latent heats? Why do they have different specific heats? What is it about them? Well, really what it is about them is the structure. In frozen form, things have a lot of structure and a lot of bonding going on, kind of like springs between the molecules or the atoms. And you have to break those springs to melt it. And then when it becomes a liquid, there's a fair amount of bonding, but it's just temporary bonds, and so they're much easier to break. And you go from liquid to gas, you have to not break so many bonds, but you do have to give the gas a lot of energy. And they don't really show it here, but the comparison of closeness to liquid to gas is nothing like this. You could have this many liquid molecules together here, and in the same amount of space you might not have a single gas molecule because they're so far spread out. And that spreading out is due to the amount of energy that you've put into them as you've heated them. And it's a lot, it's a lot of energy. But also, different materials have different structures like this. They have stronger springs. They might have stronger bonds in their liquids. They might have more bonds. They might have more springs attached to each one of them, kind of, quote-unquote springs. And so everything can change from material to material. And that's what accounts for all these different numbers that we have to put in. So, let's do a phase change now. We have ice cubes, and they're putting them into soda that's at 20 degrees. The mass of the soda is 1/4 kilogram. The ice is at 0 degrees. And each ice cube has a mass of 6 grams. So, we're putting the soda in a foam container, so we're going to assume that all the heat is going to stay in the system. It's going to go from the ice to the soda, in other words. And just like before, the heat from the ice is going to go into the soda, so the heat from the ice is going to equal negative the heat from the soda. Right? Or negative the heat going into the soda. And we're going to solve this, essentially. We're going to put in some numbers. So for the ice, we're going to do two things to the ice. First thing we're going to do is we're going to melt the ice, and that's going to require the heat of latent fusion. So it's going to be mass of ice times the latent heat of fusion. And then we're also going to change its temperature from 0 degrees to some final temperature that we don't know yet. So mass of ice times the the mass of the ice, which will be the same as the mass of the water of the melted ice, right? Times now the specific heat of water, liquid water, times the temperature change. We have an unknown thing here, this T final. And then for the soda, we have the mass of the soda times the specific heat of water. We're going to use water for soda, even though it's got some other things in it. And then we're going to have a temperature change from 20 degrees instead of from 0 degrees like it was for the ice. And then these two things have to be equal, so that you get these two things equal, and we're going to solve for the final temperature. Solve for the final temperature, plug in our numbers, and we get a final temperature of 13 degrees Celsius. So the ice did its job. It cooled down the water, right? What would happen if our final temperature ended up being negative 5 degrees Celsius? Well, that would have told us that there was enough ice there to freeze all of the soda. Can that happen? Sure, if you've ever had a big block of ice and poured soda on it, you know this. Or if you've ever had a big cup full of ice cream and poured root beer into it, you know this. Because, especially if it's a frosted mug, because you have so much cold stuff, you actually freeze some of the root beer and it's really tasty, right? But it all has to do with how much of each thing you have and how cold the ice was to begin with. In this case, the ice started at 0 degrees, so you didn't have to change the ice's temperature first. All you had to do was melt it. If the ice was at 50 degrees below 0, you'd have to first change its temperature, then melt it, then change the temperature of the water that you melted from the ice, and you would have three things on one side of the equation instead of just one. So notice that on one side of this equation we had two things we added together. The melting of the ice energy and the changing of the temperature of the water from the melted ice energy. We added those together and set them equal to the changing of the temperature of the soda. Equal and opposite, but same idea. And that's calorimetry in a nutshell. This is one of my favorite applications of these ideas. They do this in the South a lot, in Florida, but they do it even more in places like Georgia, we look further north. They do it in fruit orchards all the time. They'll flood orchards or they'll spray orchards with water. The best thing, I think, is the flooding of the orchard. So a peach orchard, for example, we get all these peach blossoms in the early spring when you have a nice warm week. And then maybe the next couple of weeks you have freezing temperatures again at night. So what the farmers will do is they'll flood their fields right before the freeze. Why do they do that? Well, what happens as you freeze water? Where does the heat that was in the water go? It has to leave the water, doesn't it? To freeze water, you have to remove heat from it. And so it goes into the air above the ground where your trees are. So if you have a big pool of water that's freezing all night long, which of course takes time and it's releasing energy all night long, then it's warming up the trees above it, right? Same thing happens if you spray the trees with water. As that water freezes, it will release its heat into the tree as well. And also the ice actually acts as a little bit of a barrier. Let's see. And so contrary to what most people understand about things, freezing is actually an exothermic process. Freezing releases energy into its surroundings. Most of the time in chemistry, when you see an exothermic reaction, you see a hot reaction, something with flame and smoke coming out of it, which is also true. It's also an exothermic reaction. But freezing is also an exothermic reaction. Thawing is an endothermic reaction. And people think just the opposite. If it's melting, there must be heat coming out. No. When things thaw, it makes it colder. And anyone who lives in a place like Nebraska knows that. The snowstorm itself, while the water in the air is freezing, can actually be quite a pleasant time to go outside when it's snowing. However, when it starts to thaw, in other words, when you have things like sleet, it's a very unpleasant thing to be outside. It's very cold because that ice is releasing its energy as it melts. And it's usually very cold the day after a snowstorm when it's releasing its energies too. The morning after can be very cold, even if the sun is out. So, a couple of chapter or two ago, we talked about sublimation, where things can go directly from solid to gas, and there is a latent heat of sublimation as well, L sub S. And that happens mostly in kind of strange materials like carbon dioxide. So how do you solve these problems? Well, essentially, what you want to do, my favorite way to solve these problems is to draw a picture. Of course, again, I always draw a diagram. And I like to draw my diagrams like this. For this last problem, it would look kind of like this. I would start with my ice, and I would actually draw an ice cube, so I remember what it is. And I would draw its temperature. I would write its temperature, 0 degrees Celsius, and I would write its mass, whatever it was. And then I would draw a phase change diagram, as I call it. We're going to go from ice to water. And the water is going to be at 0 degrees Celsius as well. Because when you change from one to the other, you don't change temperature. So you change form, but you don't change temperature. And the mass, of course, stays the same as well. But then we're going to go from this to water at some new degree, some new temperature, maybe temperature final, maybe I don't know what it is, so it's an unknown. So I draw a diagram, and for each one of these arrows, I'm going to need a different Q. For this one, it's going to be a Q of fusion. And I'll just write that down. For this one, it's going to be Q specific heat of water, right? Because it's changing the water's temperature. And I do that for each different thing. So all the heat from this one might go into, and I'll draw an arrow down to another process, might go into the soda, changing temperature. It goes from a certain degree, whatever it was, 20 degrees Celsius, and it has a mass of whatever it has, and it changes to another can of soda, and they didn't consider the can itself because they poured it into styrofoam, which doesn't absorb much heat very well. So it goes to a can at temperature final again, right, with the same mass again. And this arrow here is going to have a Q, which is going to be QC, and I usually write the equations to QC is going to, and I actually might write the Q of the soda instead of QC, and up here I might write Q of water instead of anything else. But so this is Q of soda is going to be equal to the mass of the soda, and I write the specific heat of the soda times the delta T, which is, of course, if it's delta T, then it's temperature final minus 20 degrees, right? And up here I would do the same thing for the latent diffusion. I would do the mass of the ice times latent diffusion of the ice. And then over here is mass of the water, mass of the ice is going to be the same, so I'll just write mass of ice times C water times delta T, which is going to be T final minus 0, which is an initial, right? So I know that these two, since they're all in a row, have to be added together to give me a total. And then they have to be equal to, that's what this arrow is going to represent, they have to be equal to this thing. And that's how I do that problem. I usually draw a picture first, write down temperatures, write down masses, write down equations for each transition, and then set them equal. Then add them up and set them equal. Solve for what you want to know. So that takes us into section 14.4. How many sections do we have?
I think it's 7 with the last.
Goodness, this is wearing me out.
Wow.
We'll take another break in a little while. Okay, so heat transfer methods. How can heat move from one place to the other? We're going to talk about essentially 3 different types of heat transfer methods. Conduction, which is simple. It's transfer through touching. 2 things that are touching, they're not moving, the matter is not moving. There's physical contact, and the heat goes from one object to the other through that physical contact. It says that it's stationary. That means that it's stationary on the macrocosmic scale. Of course, the molecules or atoms or things are moving around, but the actual objects are not moving. Convection is heat transfer by movement of a fluid or a gas. So as gases and fluids just naturally move because their molecules move, they are going to move heat around. They're going to be able to transfer heat around. So that's called convection. And radiation is heat transfer by electromagnetic rays, essentially. So everything that has a temperature releases electromagnetic rays because its molecules are accelerating constantly. And these constantly accelerating charged objects always give off radiation of some kind, and that radiation is a type of energy that is lost that allows the body to cool off. Most bodies are receiving just as much radiation as they're giving off, and so they never really cool off much that way. But if you could not receive any radiation and only give off radiation, eventually you would lose all the energy in your body. It would just be that way. It doesn't happen that way. Everything's always receiving and emitting radiation of some kind. That's actually why we can see each other, for example. Our bodies are reflecting and also creating radiation from the sun and from lights and from all kinds of different things, and from each other, really. And that's what our eyes detect. So one of the best ways to demonstrate all three forms of this is from a fire. And here they're not. Here they're just showing a fire, but a campfire actually you can demonstrate all three forms of heat from a campfire. If you're sitting around a campfire, the heat that you feel from the campfire is mostly from radiation, because you're feeling that heat from the side, and it's a strong amount of infrared radiation which your body absorbs very easily and turns into heat very quickly. And so the infrared radiation coming off of the fire is heating you up mostly. However, if you put your hands over the fire, you'll feel a very different kind of heat. And it's immediately apparent. It's actually quite a bit hotter usually, because above the fire you're going to feel both the radiation heat and convection heat from rising gases. And those rising gases are really hot gases. They're getting hot inside the fire and coming flying up out of the fire. They don't fly sideways much, mostly straight up. And so you get convective heating above the fire. Now, the conduction heating from a fire is something that we don't get much of. Usually it's secondhand, but you can get it directly from the fire. You just have to reach your hands into the fire and touch something that's burning, right? Most people don't do that, or if they do, they're doing it very quickly to rearrange things in the fire or put something in the fire. But we've all experienced it at some point, touching something very hot. But also, the radiation and the convection from the fire can heat objects around it, and then you can touch those objects and you can feel that conduction of heat. So here they show a fire in a house and how it heats a house. And the best way to heat a house is to have lots of airflow so that you can take advantage of convection. But you also get conduction. If you have if you have a fireplace that's built well, it'll have a place where underneath it's got a great big hearth, a great big stone platform usually, and that hearth gets hot from the fire, and then it heats up the surrounding room by touching the carpet, by touching the floors, by touching the air in the room and other things like that. Also, the chimney in a good, well-designed fireplace will run the entire height of the room, so that as the chimney heats up from convection and from conduction and from radiation, it heats up the room as well. You know, the bad side of it is also heats the outside, because some of that heat can go to the outside of the house, the outside of the chimney. But the convection of heat leaving the fire upward draws air into the fire, which makes the fire burn hotter, right? And actually, the longer the chimney, the higher the chimney, the more it will draw. It's kind of an interesting effect. The more it will draw air in, and your fire will be hotter, so all these things will work better. And so you have to be able to have airflow in the room. If you have the room all sealed off, you won't be able to start your fire. Some fireplaces like mine is designed to draw air from the outside, so that you're not sucking, so you don't have to have windows open and other things in your house. So I actually have on the back side of my fireplace, down here low, beneath the fire where the fire is, there's actually a vent here, and a lot of fireplaces are built this way, where it draws air in below the fire, and the air comes up underneath the fire. It makes a very good, it draws nice convective air. It's very useful, these things. So conduction. There's actually, things that we don't want to conduct, and usually that's walls in your house, and that's why they put fiberglass or foam or other things in the wall, is to prevent conduction. Why? Well, because wood and gypsum board, which is the sheetrock, they actually conduct heat fairly well. Heat goes through them nicely, which is a bad thing if it's hot outside, or if it's cold outside, you want to be the opposite on the inside. So they put in gaps in the wall. They don't just have a sheet of wood for your wall. They have a sheet of wood on the outside, and then they have a gap, and then they have something on the inside. Because air that is not moving does not transfer heat very well through conduction. And convection is a very slow process. But even better than a gap of air is actually a gap filled with things like fiberglass. There are actually lots of things that are very good for preventing heat conduction. But the idea is to fill the space with a material that doesn't like to transfer heat very easily. And so fiberglass is one of them. Foam is another one. Another thing, so here, what matters for conduction? It turns out that for conducting heat, the things that make the difference are the material that it's conducting through, and the distance that it has to go through, so how much of the material the heat has to get through, but also the cross-sectional area of the material, and the difference in temperature. If it's super hot outside, heat will travel more easily through the walls of your house because the temperature difference between outside and inside is greater. So it's actually the temperature difference that matters. And it turns out that for all these things, you can calculate a rate of heat exchange, which is kind of like the speed of heat or the velocity of heat movement through the material, as equal to the area times the temperature difference divided by the distance that the heat has to travel, all multiplied by thermal conductivity, which we call K. So for materials that heat travels through easily, like metals, K is going to be a very high number because the heat transfer is going to be big. For things that heat doesn't transfer through very well, like foam, K is going to be very small.
If you have two different things, there are two different Ks.
Yes, you have two different things, you're going to have two different rates. One for the first material, one for the second material. So here we have a styrofoam box. Ice box has a total area of 0.950 meters squared. Walls average thickness of 2.5 centimeters. Box contains ice, water, and canned beverages at 0 degrees Celsius. Inside of the box is kept cold by melting ice. How much ice melts in one day? The box is kept in the trunk of a car at 35 degrees Celsius. So essentially the amount of heat that is going to travel through the box is going to be the amount of heat that the ice is going to have to provide as it melts, or suck up as it melts, right? So, so the things that we know the area of the box, they told us that. We know the distance we have to travel, 2.5 centimeters, convert. That, we know the temperature change, it's going to go from 0 to 35, because that's 35 on the outside of the box, 0 on the inside of the box, right? And the time is going to be 1 day, which is going to be 86,400 seconds. So all we need to do now is figure out how much ice is going to melt trying to keep this stuff at 0 degrees. Well, we can calculate how much heat is going to transfer out per second, Q per T, which is the heat transfer rate of heat transfer. That's K times the area times temperature change over distance. We have all those numbers. So we're going to lose 13.3 joules per second after we plug in those numbers. 13.3 joules per second. If we're going to keep this cold for a day, then we need to divide our rate by the time, the 13.3 joules per second divided by this number of seconds here, and that will give us, multiplied by the seconds, and that will, then that way the seconds will cancel and we'll just have the amount of energy that we're going to lose in the day. We're going to lose 1.15 times 10 to the 6 joules of energy. So we need enough ice melting to provide that amount of energy. Well, so we plug that into Q for our equation for melting ice. Q equals mass times LF. We rearrange that to solve for mass. Mass equals Q divided by LF. The Q is the amount of energy we need to provide from melting ice. This LF sub F is the amount of energy provided per kilogram of ice from melting. And we get 3.44 kilograms. That's a fair amount of ice. It's like 15 pounds of ice to keep your stuff at 0 degrees all day long. Right? So what do? Well, you get a thicker cooler. You get a better cooler. You don't have to have much ice. Or you use dry ice, because it's a lot colder and it'll start at a much lower temperature. Of course, dry ice doesn't melt into water, and water holds a lot of energy, so that's one problem. But anyway, probably a bigger cooler is better, so you can hold more ice and have thicker walls, right? So here we have thermal conductivity for lots of different materials. You can see here, thermal conductivity really plays a role when you're talking about cooking materials as well. It's not just how much heat. You don't want to just have something that takes a little bit amount of heat to heat up, but also something that conducts heat very well when you're cooking in the kitchen, right? So really your best pans would be made of silver, but who's going to cook in silver pans? However, copper is good, almost as good as silver, much cheaper. Gold is almost as good, but way more expensive. But aluminum's not bad. You know, it's half as much as silver. It's a little bit less than half as much as copper, but it's still pretty good. Iron, not so great, but cast iron is a little bit better because it has more air in it. So anyway, down feathers, 0.025, very, very small. And in fact, they've not really been able to make a better material that's a fake material that makes a better sleeping bag than down. You could fill it with fill your sleeping bag with styrofoam, but styrofoam doesn't compress very easily. Whereas down feathers can compress to super, super tiny and still fluff up to make a very, very nice insulated thing. So there are, you know, when you go climbing Mount Everest or other things like this, you're still wearing a coat that's filled with goose down, just like 100 years ago when they were doing these expeditions, because it's really the only thing really warm enough to handle those temperatures, and your sleeping bag's still made of goose down up in those mountains. So I have two goose down parkas, and a goose down sleeping bag made by Western Mountaineering. They are as warm as you can possibly get, I'll tell you that. The only time I've ever had to sleep in my sleeping bag was when I was sleeping, I actually had to close it up when I was sleeping at 15 degrees below zero with a wind chill factor of -40. It's the first time I ever got cold enough to actually have to get inside the bag all the way. And I was not cold once I was in it, that's for sure. Okay, calculating temperature difference maintained by heat transfer. Conduction through an aluminum pan example. So we have a water boiling aluminum pan. Sauce has a bottom 0.8 centimeters thick, and it's 14 centimeters in diameter, so that'll give us our area, some calculation. Water is evaporating at a rate of 1 gram per second, so that'll tell us how much energy we're putting through the pan, because that much energy has to go into water, right? 1 gram per second is going to be 1 calorie per second, so that's going to tell us something. So, first of all, we can rearrange our equation for temperature, for heat transfer rate through a material. So the rate is on the right side with the thickness and the K in the area, and then the temperature changes on the other side. Convert some things into SI units, calculate the area of the pan. Look at the thermal conductivity of aluminum. And then heat from vaporizing water. Right? Heat for vaporizing water, 2256 joules for each kilogram of water. We're going to need 2256 joules per second to do 1 gram of water. So it's quite a bit of energy, actually. So we need 2256 joules per second, or 2.26 kilowatts. So that's our Q over T. You plug that in for Q over T, you plug in your distance in meters, you plug in your K times your area in meters, and you get a difference in temperature of 5.33 degrees Celsius. Convection. So that's conduction. Now we do convection. Convection is essentially flow of fluid, flow of gas, and a lot of it is due to the fact that when you heat it up, it moves faster, right? So it's going to move, as it moves faster, it's going to move around more, it's going to come in contact with other molecules, and you're going to get lots and lots of heat movement. However, it's still a slower process than conduction for the most part. Depending on the situation, depending on the temperature change, how much drastic temperature change there is, I guess. But convection. So, unlike conduction, there's not really anything that we have to calculate any differently. With conduction, we have this equation that involved area, involved distance. With convection, there's not really anything like that. It's much more random, so doing the math of it is going to be very difficult. And so instead of doing the math of it directly, we're just going to do it indirectly. So for example, in this example here, we have a house where the air goes in and out around doors and windows because they're not perfectly airtight. And the air in a typical house is completely replaced in less than an hour. So we're going to suppose a moderately sized house has these dimensions, and all the air is replaced in 30 minutes. We're going to calculate the heat transfer per unit time and what's needed to warm the incoming cold air by 10 degrees Celsius. So in other words, we know how much air is moving in and out in volume, and we're going to calculate how much energy it takes to heat up that much air. To calculate that volume of air, we of course we're going to need the mass of the air, but we're going to need rho times the volume. The volume is the dimensions of the house multiplied together, and the density of air is 1.29 kilograms per meter squared. So it's 836 kilograms of air every hour that we have to heat. We have to increase in temperature by 10 degrees to make it nice because it came from the outside, which is colder. So to do that, we're just going to use our change of temperature equation for heat, which is the specific heat equation, right? You use the mass of the air, the specific heat of the air, and the 10 degrees Celsius that you're going to change it, that change in temperature, and you get the answer. Pretty straightforward. Calculate kilowatts, you take the amount of heat divided by the number of seconds you're doing it in, which is 1800 seconds, it turns out. Okay, so what has this got to do with wind chill factors? Well, wind chill factors are actually, they're essentially how much colder things get when the air outside is moving in the wintertime. Because when the air outside is moving in the wintertime, the cold air goes across your body more often and removes more heat per second from your body. If the air is still, then your body heats the air around it, and it kind of comes to an equilibrium. Your skin still gets cold, but it gets to a point where the heat, leaving your arm has heated up the air around you enough that it's no big deal. That it's not transferring as much anymore. You're not as cold. Wind, you never heat that air around you because you're always getting fresh, freezing cold air, right? Also, humidity can make a change in that as well, because water in the air removes more heat from the body than dry air does, right? So that's where you get that wind that feels like it's cutting through your clothing. So here the moving air temperature for if you have wind speeds, different wind speeds, you have different temperatures. But what they don't have in here is the humidity factor. This is how animals stay warm and humans with their hair. You get convection currents, we call convection loops inside the fur, which keep it warm, actually. And it's full essentially because it's pockets of air in the fur, right? Kind of interesting. The cold outside and the warm inside create these currents. You ever seen a polar bear? Polar bears have actually black skin, and their fur is made of tubes. Their fur is tubular, so it's hollow filaments of hair. And those hollow filaments actually gather the sunlight, radiation heat, and the radiation bounces inside the tube, kind of like a fiber optic, and it goes all the way down to their black skin. Well, their black skin absorbs almost 100% of that radiation from the sun and turns it into thermal, or into, it turns it into infrared light that gets trapped in their fur by these tubes. And so they're kind of like their own little greenhouse system. They're white fur with these, it's actually clear, their fur is clear, but the tubes of fur let in all the light from the sun. The black skin releases radiation that gets trapped in the fur, and that radiation keeps them extremely warm. Other animals do similar things. Instead of using radiation, they use insulation. They use things like feathers with penguins, feathers and oil with penguins. Ducks do the same thing, and geese. But they also use lard in the case of like the walrus and seals and other things like this, because it's a good insulative barrier between them and the cold water or the cold ice that they're in. Here we're going to talk about convection away from the body as you sweat, right? So an average person produces heat at the rate of about 120 watts when they're at rest. At what rate must water evaporate from the body to get rid of all the energy? So at rest, 120 watts you can handle. Your body can just, your body essentially can radiate that away and convect that away. But at some point, you're going to actually have to sweat water onto your surface of your skin so that the hot surface of your skin can release its energy by evaporating that water, by cooking the water off of your skin. And so how do you do that? Well, it's the rate of heat, Q over T, is going to equal the mass of the water times the latent heat of vaporization over T, 120 watts, 120 joules per second. And we solve this all out, and we get mass over time equals 120 joules per second latent heat. And then we plug in our numbers here for latent heat of vaporization of water. And it turns out that for just being at rest, you're going to have to sweat off about 2.96 grams per minute, or have some kind of evaporation at 2.96 grams per minute. That's not much water, it's no big deal. However, if it's very humid, the sweat may not evaporate because it may not have anywhere to go. If the water in the air if the air is very saturated with water, it doesn't want, your body doesn't want, the water on your body does not want to go into the air. It's very hard for it to get into the air. And this is a problem. So high humidity, people will sweat, but the sweat doesn't do its job. It doesn't cool the person off because it doesn't evaporate from their skin. So very, very hot, humid climates, you're in a great danger of overheating because because your body will not cool. It's not evaporating that off your air. And in very, very hot, dry climates, you have just the opposite problem. As soon as the sweat hits your body, the heat on the outside, the heat in the air, evaporates it very quickly instead of the heat in your body. And so you have to sweat more. And so your body is sweating more than it needs to, and so you get dehydrated, right? And when you get dehydrated, then you can't cool yourself off anymore. The one is called heat exhaustion, the one that happens in very, very humid climates, where you get your skin essentially gets very cold and clammy, or very hot and clammy. It can be either way, actually. But your body temperature is very high because it's not being allowed to release. And then in the other case, you get very hot and dry skin, and you still have that internal body temperature that can't be bled off. So how do you fix both of them? Well, for the heat stroke, which is the second one, you drink a lot of water. You always drink a lot of water, and you get salt in your body that will help to retain more water so that you can drink more water, get more water. For heat exhaustion, you just have to cool them off. And you essentially bags of ice, get them in the shade, put them in a refrigerator, whatever, because the sweat isn't doing the job. It's not that they haven't got enough water in their body, it's that the water just doesn't do anything because there's too much water outside. Lots of different interesting situations. So radiation. Radiation is essentially different types of light. Ultraviolet, ultraviolet is a type, infrared is a type, all the visible light colors that we see, but also everything on either end of the spectrum going all the way to gamma rays and other things. It's all radiation. The one that we normally associate with heat is infrared, because the infrared is the type of radiation that our bodies absorb very well, and the Earth absorbs very well and turns into heat. But it's not the only kind of radiation that can turn into heat. Everything that gets hot radiates. And this chart here shows how much light things can radiate, kind of in general, and at what frequencies they radiate, what wavelengths they radiate. So when things get extremely hot, 6,000 Kelvin, they tend to burn more white hot, as we call them. Why is it called white hot? Because the light coming from them is generally very white. Looks very white. And I think 6,000 Kelvin is very, very hot. And it is in the visible range, but it's all of the different light from the visible range. So when you mix all the colors from the visible spectrum, you get white. And it's very intense. You can see it's very, very high peak. That means there's a lot of radiation coming out. As things are cooler, let's say about 3,000 Kelvin, this lowest peak down here, you still get some stuff down in the visible range, but most of it's towards the right end, or the long end of the visible range, which is the red end. And so that's when we call things red hot. In between, they can be yellow and green and blue hot, at 4,000 and 5,000, whatever, Kelvin. But then as you get cooler and cooler and cooler, you get a shift out here towards the longer and longer wavelengths, into the infrared and the radio waves and things like this. And this is actually how they can tell how hot things are out there in space, how hot stars are, planets and other things. They emit at different in different spectrums and with different curves like this. There's actually a very interesting consequence of this that we talk about in the second semester, called the ultraviolet catastrophe, as things get super, super hot. And it led to actually led to a revolution in science a little bit. Here they show two different sidewalks, one kind of a concrete sidewalk, one a black sidewalk. In the concrete sidewalk, the ice melts slower than it does on the black sidewalk. And the reason for this is actually related to that ultraviolet catastrophe. It's the absorption of energy. It turns out that lighter materials reflect more energy than they absorb. Dark materials absorb more light than they reflect. They both can emit lots of energy, but when you're darker colors, you have a tendency to absorb and emit more wavelengths. So we call this black body radiation. and it's called black body because things that are black in general absorb in their cold state when there's no heat going on. If they're more black or darker colors, things tend to have the ability to absorb and emit more light, and so they have the ability to melt things faster as they get hot. Things that reflect light a lot don't absorb as much, don't emit as much, and don't heat as much. Here they talk about those different things. So here we have just a black material, absorbs a lot of energy, reflects very little bit of energy, and after it's absorbed a lot of energy, it emits a lot of energy as well and retains very little of it. And people think, well, if things like clothing absorb a lot of energy, then when it's hot outside, I don't want to wear black clothing because it would absorb a lot of energy, but it also emits a lot of energy. So it actually does not matter that much what color your clothes are as far as the radiation energy. With something that is white, for example, that reflects energy, people think, well, that looks cool, it looks light, but actually you get a really funny effect. So this is a piece of material that is silver coated on one side, and it reflects a lot of energy. It's got this nice light color on that side, but on the back side it also reflects a lot of energy. So if you're wearing a white shirt or something, and you're thinking that's keeping you cool because it's white and it's reflecting the light off, well, the heat from your body is also reflecting back into your body and off that shirt. And so white shirts are not actually ideal for this. It's actually darker colors are more ideal, and you can see that when you go to the Middle East. The Middle East, the burqa that women wear, for example, where it covers them from head to toe, is made of black material. Not because they're mourning, but because it's covering their entire body. If it's made of anything else, they die. It's just it's so hot there in the summer times. You much prefer to have something that can absorb and re-emit. Get it off of your body. And if it's loose clothing, it's actually a very good idea. If it's tight clothing, you get some other different effects going on with conduction that you don't want to happen. Because once these things absorb this light, it turns into thermal energy inside the material. And that thermal energy can be conducted to the body. So you don't want any of the materials, you want as few of the materials touching your body as possible. But anyway, there is an equation that is involved with radiation. And it's not something that we're going to figure out on our own. It's something that is coming from quantum mechanics. But the amount of heat transfer through radiation has a few things involved. It has this sigma thing, which is the Stefan Boltzmann constant, 5.67 times 10 minus 8 joules per second, meters squared, Kelvin per fourth. And then you have the area, the cross-sectional area, or the area of the emitting or absorbing material. Then you have the temperature in Kelvin raised to the fourth power. But then you also have this little E thing here called emissivity. And that's how much of a black body it is, or how much it absorbs or reflects light. And so every material has its own number for that. And here you can actually see a building that is emitting light, and the brighter colors, like the reds and the yellows, are where there's, wait, is that right? There's a darker. Let's see what it says on the caption. Yeah, I guess the yellow is where it's the most heat coming out. And so you can see here in the windows you got this yellow. But red is also pretty high, and there's lots of places where there's red and yellow next to windows and around window frames. And then the blues are where you have the least amount of heat coming out, least amount of radiation heat coming out. So how are we going to use this Stefan Boltzmann equation? Here we have an example where we're transferring heat by radiation. We have an unclothed person standing in a dark room. Ambient temperature is 22 degrees Celsius in the room. Person has a skin temperature of 33 degrees Celsius, surface area 1.5 meters squared. They give us the emissivity, that's the E. The Stefan Boltzmann constant sigma stays the same all the time. And we want to calculate the rate of energy loss by the person, right? So we plug in all our numbers. It's just simple as that. And we get negative 99 joules per second, or negative 99 watts. Of course, the bigger the temperature difference, the more heat exchange you're going to have, and that's true in all situations with heat exchange. So, what is global warming, otherwise known as the greenhouse effect? Global warming is a natural consequence of having the atmosphere that we have and the sun that we have and the earth that we have. It is not anything that has been created by man or by cars or anything else. It's been here the entire time. The earth has been here just about. And thank goodness it has been, because without global warming, none of us would be here. Global warming is what makes life possible on any planet. Runaway, extreme global warming is a bad thing. That's what's happened on Venus, for example. But what happened on Venus was also natural. They naturally have a very bad atmosphere for life because it traps too much energy and essentially never cools off. The Earth's is just right, however. We get ultraviolet light, visible light, infrared light, all kinds of light coming in, including radio waves and everything else, gamma rays, all these things coming in from the sun and from space, and they enter our atmosphere without much trouble. Some of this stuff is bounced off into space, off of clouds and off of nitrogen in the atmosphere and other things in the atmosphere, but most of it comes in pretty nicely. We get infrared that is fairly high frequency infrared coming in, and it's very close to being red. And there's some infrared that doesn't make it in the atmosphere. It gets what we call scattered. It gets bounced off the atmosphere. But we get a lot of the radiation from the sun actually does come and reach the Earth. And as it reaches the Earth, not just in the ocean but on land as well, it gets absorbed for the most part. A small amount of it gets reflected, but most of it gets absorbed. The Earth is a very good black body. If it had no heat in it, it would look pretty much black. So it's a very good black body. So it will re-emit almost all of this energy. It will absorb some of it, will absorb all of it, but it will also re-emit almost all of it. Okay? And it gets re-emitted, however, along a very narrow bandwidth. Most of the light that gets re-emitted as an infrared wavelength that's fairly long. And it just so happens that carbon dioxide in our atmosphere, which comes from living things breathing, right? Carbon dioxide in our atmosphere reflects that infrared back down to the Earth. And so it gets absorbed again, and then emitted again, and absorbed again. Well, this is a great thing, because during the day we get sunlight, and it heats up our Earth through this absorption and re-emission. But at nighttime, it stays warm. Why? Because that energy just keeps bouncing around. It keeps getting reabsorbed and re-emitted, and reabsorbed and re-emitted. So at nighttime, we're not at 400 degrees below zero, which is good, I think, because that's what happens on the moon, where there's no atmosphere. When the sun goes down on the moon, it literally goes from 400 degrees above zero to 400 degrees below zero. And there is no life on the moon, and there will never be because of that. You have to have a mild temperature in the day and a mild temperature at night, and our atmosphere allows for that. It's a beautiful thing. It's called the greenhouse effect. In Venus, Venus allows all the light in and lets almost no energy out. And it just has been heating and heating and heating and overheating. And it also has a fair amount of internal things going on. And that's because I think it's methane in their atmosphere. Methane gas, which is of course natural gas, is it's a very good greenhouse gas. It allows all kinds of things, and it's much better greenhouse gas than CO2. But anyway. Here they're actually using this same idea to cook food. Essentially they just make a big reflector of it, and then they cover it with clear material, so that it lets in a lot of light, and then everything in there just gets stuck in there. The light in there gets absorbed and reflected around and heats up and heats up and heats up. Just by having it sealed up, it keeps most of it in. And I guess that's it for this chapter. So anyway, one of the things that most books, this book is actually fairly nice because it doesn't get into the politics of greenhouse gases and greenhouse emissions and greenhouse this and greenhouse that. But most of the textbooks that you'll see in physics or engineering will cover that. It'll be like its own chapter almost. But I'm kind of glad they don't, because it's important to not get involved in the politics of science if you're going to be a scientist. The politics of science lead scientists astray. And there are people out there, I mean, the greenhouse effect is a physics effect. But the people who have made their living off of telling people that the greenhouse effect is ruining our planet will not listen to physicists, because they say that they're not climatologists. But climatologists are essentially just a very narrow branch of physics. They don't know anything more than physicists do. And they're doing all these experiments without any physicists watching over what they're doing. And they've actually been found to be lying. All of the greatest ones that started the movement, it was found out just a few years ago that they made up their results. And why did they make them up? They made them up because they saw that politicians were jumping on this, and that's where all their money came from. It all came from government. Most research money in the United States and the world comes from governments. So if the politics are going one way and you see it, you can really take advantage of it. It's unfortunate, but it's true. And so science almost always follows politics and all the hot buzzwords of politics. And these people just took advantage of government. And when they retired, they didn't see any reason to hide what they'd done. Why would they hide what they'd done? It's not illegal. It's not illegal to lie in a scientific paper. It's just unethical. Nobody's going to arrest you for it. But they made millions off of it, literally, off of our tax dollars, just lying in their work. It's not to say that we shouldn't watch what we're doing with our cars and with our power plants. We should. And it's a very real situation. But the scare tactics they used were predicting that by the year like 1998, the entire world would, the entire United States coastal region on the east coast and the west coast would be covered with water, and New York would be 30 meters underwater, and San Francisco would be completely engulfed, and all these things. And they said all of those things as a lie. They knew they were lies just to get the money. And that was money that could have been used to feed the world. I mean, we could have put that money into cancer research or into food production research, agriculture research, and we could have stopped the plagues in Africa, and we could have probably cured Ebola, and we probably could have fixed the drought in Ethiopia. But we didn't. We were too busy talking about in 20 years the Earth's going to be underwater because of the polar ice caps melting and all these things. And they lie to people. They lie to people who don't understand science all the time. They say that the North Pole, the North Pole is melting, and that's going to make the ocean rise. Well, the North Pole is a big ice cube sitting on top of the ocean. And if it melts, it'll actually make the ocean go down. It actually displaces more water as an ice cube than it would as water. We know this, put ice cubes in water and see what happens. They're less dense than water, they make the water rise. It's the ice cap on the South Pole that's the problem. That one's actually growing, not getting smaller. If that one melts, it would make the oceans rise, but it's actually getting bigger than smaller. And they've even lied about that, because there's one part of it, one very small part of it, that's getting smaller, but the rest of it's getting bigger. But the only place they measure is the one that's getting smaller, because that's where they want their results. They don't want anyone to know that the rest of it's getting bigger. So they say, well, 10% of it is shrinking. What about the other 90%? Well, we're not going to tell you about that. We're not going to talk about that.
You can't find it.
No, they just say, they just don't even do any, they don't do any research. It's not even that hard to do the research. I mean, the satellite pictures are available for everyone to see. It's pretty easy to measure because when the ice caps get bigger, they grow on the satellite. They get longer on the satellite. So anyway, it's just an interesting. It's an interesting thing about science that exists in just about every realm of science. There's always politics somewhere that are going to affect what people are doing and saying, and unfortunately, it creeps into so many classrooms. You have English teachers preaching against gasoline cars, and they really don't even have a clue what they're talking about, but they think they do. You have English teachers preaching about this and that and the other, all these science things, and you have history teachers and social science teachers, high school teachers preaching about these things because it's become so political, but they don't have a clue what they're talking about. They have no idea if the science is good or bad, but they don't care because they've been told this is good. It is good. It has to be good. It's a shame because we end up wasting a lot of money and resources